The broadcast is now starting. All attendees are in listen-only mode.
So, good evening everyone. This is Fabio Tiriticco speaking from Amsterdam. And thanks everybody for joining this webinar tonight. And thanks, of course, to the Code Emotion guys for facilitating this. I think everybody can hear correctly. Yeah, it seems like it. All right, so before we dive into this webinar, one thing that I want to mention, if you want to ask any question, please do that via the questions panel in the GoToWebinar app. We'll just can write them anytime there, and we'll pick them up at the end of the webinar. All right, so let's dive in. First, a little bit introduction about myself. That's me. Pretty much everywhere on the internet you'll find me by the handle of TicoFab, and I work in Amsterdam as a tech lead and software architect for the company that you see in the bottom right corner of that slide. It's called Vir Online. We do everything that has to do with weather, so weather forecasts, rain, temperatures, you name it. It's a lot of data processing in the back end, so quite suited for some reactive technique. And another thing about myself is that a while ago, I got so fascinated by this reactive concept that I founded this Reactive Amsterdam meetup. We host regular meetup, and we've been quite successful so far. We've been sponsored by big companies. Uber is one that has sponsored us quite a few times. So if you're around Amsterdam, make sure that you join us. The next one is scheduled for the 21st of February, and it will be focused on Kafka, CQRS, domain-driven design, and a couple other nice things. So let's get down to some action. The outline of tonight will start, well, first bring some clarity about this word reactive, which I know sometimes can mean all or nothing, and you hear it in many different contexts, so we'll try and shed some light there. And after that, we'll look a little bit deeper into some so-called reactive patterns and a couple of quick code examples how to implement those. Let's start with reactive programming then. If we try to summarize the concept of reactive programming in a few points, we can say that it is for sure an event-driven approach to data processing, where problems are decomposed into multiple discrete steps, which are then executed asynchronously, and all this asynchronicity happens generally in a callback-based fashion. Let's immediately give a little example on some code. And let's look at one of the most popular reactive libraries, that is the RX extensions. And in this case, we're going to look at a reactive Java, RX Java extensions, and in a way that you could use it, for instance, on an Android device. So let's say we have a list of objects. In this case, we have a list of cats. Then the observable class in the RX Java library has this static method called from that takes a list as an input and will basically output the list items one by one. So from those cats, a list of cats, we will generate a stream of cats, a stream of data. Each item will be put into the stream sequentially, one by one. And once we have created a stream like this, we can apply some operators to it. For instance, we can filter an item. So in this case, that inside the filter parentheses, you have a lambda from Java 8. So in this case, what this item does, what this operator does, it will propagate through the streams only cat that satisfy that condition, so only white cats. After that, we can apply a map operator, where basically for each cat, we are going to fetch its picture. The internet is usually full of cat pictures, and then return this picture. Subsequently, we can apply another map operator where we take one picture and apply a filter to it. At the end, we will be able to subscribe to this stream, and that will be our sort of final statement there, because we will receive a filtered picture after it's gone through all the processing steps of the stream and display it. Now, there's one more thing I want to mention, is that these libraries, I said, they are very useful to do asynchronous processing. That means, in an environment where concurrency, threaded operations can be done in a concurrent and threaded way. Well, this library makes it really easy, as we can just add that operator, subscribe on. That means that everything that comes after that operator in the stream, every step, will be executed on a new thread. When we get at the end of the processing and we want to do something on the original thread, we can just add this observe on operator. And well, what's inside it is a bit of an Android specific thing that basically will retrieve the results of the processing, and the final subscribe step will be executed on the main thread. So if we look at this little processing that we have written here, and we can easily see what are the main benefits of using this kind of reactive programming. In particular, conciseness, and it offers us a stream-like processing. So we can do a lot in just a few lines of code. It simplifies our life with parallel or threaded work, because we've seen how easy it is to switch threads. No more, old-style Java locks and synchronization issues. And also, there's a third benefit, that is easy management of back pressure. Now, back pressure, I will just introduce it very, very briefly. The idea of back pressure is that when you have such a stream, at some point, some consumer down the stream maybe is able to process things slower than the producer puts it into the stream. So, for instance, in our cat stream, probably, let's say that the filtering is a very slow operation at the end. And then this slow consumer is able to tell to the producer, hey, please slow down. I can't cope with such a rate. And so the stream will just slow down so that items are propagated at a speed where the consumer is able to process them. Now, I know this is a very quick introduction to the concept of back pressure, but it is really crucial in real life. So maybe go give it a look for yourself. Now, this offers us a nice bridge between reactive programming and reactive systems. So, and before we do that, I need to introduce a little bit of difference between an event-based system or a message-based system. Basically, events are really just facts for others to observe. So in an event-driven systems, components actively listen to an event queue. They listen all the time, and as soon as there is an event on the queue, they consume it and react to it. In a message-driven system, instead, messages that are sent have a clear single destination. So one message is sent directed to another component. This means that not only the person who, the component that sends the message knows who is going to consume it, but also that on the other end, the sender is known. So the recipient of the message knows who sent that. And as you will see, this will enable us to do a lot of different things. Message-driven systems are usually a peer-to-peer networks where components communicate directly with each other. And one first important difference then is that an event-driven system focuses on addressable event sources, where everybody looks at. For instance, unobservable, you could see that as an event source, while a message-driven system focuses on addressable recipients. So where every component will have, an address, a name, something you can identify. Now, in the context of reactive systems, what are the benefits of asynchronous messaging? Well, first of all is the separation between components. Think about it, with a real-time image, for instance. If you send me an email, we are not coupled in any way. You have sent me this email, and then you can go on to other things. We are totally decoupled in that. And one first benefit of this is that the error containment is really easy at that point. Because again, in real life, if you send me an email, and that very night I get, let's say, a heart attack, you're not going to get one yourself. You are completely separated. Now, please, by the way, and nobody sends me an email tonight, please. And so, and then one third benefit that I can for surely mention is that the domain mapping comes closer to reality. Because if you think about it, in reality, we don't really share our state with someone else. The way we interact with each other is through communication. So we send messages to each other. We don't look into each other's brain and read the value of a variable. You ask me what's going on. That's a message, and I will reply with another message. So message-based systems, in the end, bring us really closer to reality and the way we can model our systems. Focus shifts from class diagrams or interface definitions to the message flow, that is, how components communicate with each other. What's the protocol that defines the conversation between components? Who says what and when? Now, this bridge is very important because now we are going to define the actual traits of a reactive system. These traits come from the Reactive Manifesto, which is a manifesto that was written in 2013 by a group of people, among which the founders of TypeSafe, now called Lightbend, the company behind Scala and Akka and a few other things that you might have heard of. We're going to see them a little bit closer down the line. But anyway, so this Reactive Manifesto defines that a reactive computer system must react to its users. That is, has to be responsive. So what does this mean? It means that a reactive computer system should always try to be available. Even in case of failure, we should stay available, maybe offer our users a degraded version of our service, or maybe even just a message saying service unavailable is better than no response at all. When you go to a website and there's a timeout and you never get a response, that should never happen. And by the way, by user here we mean not only human, not only a human person that looks at a website, but it could also be a web service that is accessing your APIs. That's another case of users. So the second trait is that a reactive system should react to failure and stay available. In one word, it has to be resilient. Now, resilience is defined as the ability of something to jump back into shape after a failure. Resilience means to restore functionality into full capacity and not just, crawl on. We want to heal fully. This is different than fault tolerance, where fault tolerance is really the concept of, getting hit, but still survive and keep going, sort of like, Schwarzenegger in some movies from 20 years ago or something. The problem with fault tolerance is that on the long run is not a sustainable strategy. Our internal state gets messier and it becomes more and more difficult to recover. So resilient components instead, they are able to self-heal fully, start fresh. Let's say we'll see more about this in a little bit. Another trait is that reactive systems need to react to varying load conditions. That means, in one word, they have to be elastic. If you think about big systems, there's almost always a traffic variance during the lifetime of a service. Think about an online shop, I don't know, Amazon. What happens is that they might have more traffic before Christmas, so there's a seasonality variance there. Or maybe think about a banking system. Maybe at the end of the month you have payday, and so a lot of traffic, a lot of requests. So you have these traffic peaks. Now, to face such a condition means that your system needs to be able to scale out on demand. So allocate more resource in order to cope with the increased load, but also to shrink down or scale in once the peak has gone. And the idea is use just the right amount at any time. You don't want to keep useless resources running for efficiency reasons, especially nowadays when you run on a cloud server. The costs add up, and really want to be as efficient as you can. So that's elasticity. And then the last trait is a little bit of an odd one. It says that a reactive computer system must react to inputs, or well, its components must react to inputs. And that means that it has to be message driven. This builds on what we've just said earlier about message driven systems. And in a sense, as we will see in a little bit, this message driven characteristic enables all the rest. Actually, if we want, we can show better this diagram and these values in this other figure, where from the top you have the values that we want to achieve. We want a system that is responsive, maintainable, and extensible. And we get there by being elastic and resilient. And we can achieve this because we're message driven. If you want to sum it up in one sentence, you could say the reactive systems strive to increase productivity and make sure that development and maintenance of components reduce the accidental complexity to a minimum. At this point, now you might have these ideas a little confused now about these reactive systems, but now we'll come to some examples and implementation that will make everything clear. At this point, we can then already sum up a little bit this idea of reactive programming versus reactive systems. How do they relate to each other? Well, reactive programming, to start with, what we've seen is it's an implementation technique, which is good for asynchronous data flow management. And it's mostly applicable to a single node or service. So there's some locality in here. And all in all, it's most useful for developers. Reactive systems, on the other hand, are a set of design principles that are good for orchestration of complex systems. So think about data consistency, cross-node communication, coordination of components, failure management, and fault, all the separation of concerns and responsibilities, and so on. And so at that point, the applicability of these principles are really about the entire system that we are managing. And in that sense, they are most useful for architects. So we can say easily that reactive programming is an important part of a reactive system at a more local level. Now, in order to explain a little bit better these reactive system principles, we are going to do a little overview of a couple of simple reactive patterns. So these so-called reactive patterns are design patterns to achieve those reactive principles that we've just seen. And toolkits exist to implement these patterns. In these examples that follow, we'll use Scala, the programming language, coupled with akka, which is a toolkit that offers many implementations ready for you to use in order to achieve these reactive principles. From my experience, I have to say akka takes the pain away from working with complex concurrent systems and brings back some sanity, if I can say it. Let's move to the first reactive pattern. Reactive pattern, simple component pattern. One component should do only one thing, but do it in full. The aim is to maximize cohesion and minimize coupling between components. Now, how does akka implement this? akka relies on the actor model, where an actor is an isolated component that contains state, so some internal state. It has a mailbox to receive and send messages, the messages that we mentioned earlier. It contains behavior logic, so an actor is able to execute something or to do some processing. And most importantly, an actor has a supervisor. The supervisor is especially important for error containment and resilience, because you will see that such a structure makes complex parallel processing tasks simpler and provides building blocks for resilience, as we'll see in a moment. What's important here to take is that actors communicate with each other exclusively through asynchronous messaging. So remember the mail, the email that you sent me earlier. That's the idea. And oh yeah, here's the supervisor. So actors have a parent or supervisor. If you want to look immediately at an implementation example, let's consider this very simple idea. We have two actors, ping actor, pong actor. They will send a ping, the ping actor will send a ping, and the pong actor, not surprisingly, will respond with a pong. The difference between ping and pong is that the pong message will carry some information with it. In this case, just an integer, just a number. So if we want to look at how it's done in code, let's see. This is this is in my IntelliJ IDE. This is my Scala code, and we're looking at the ping pong app file. It's only one file. The way you define an actor is after you've imported things from the akka library, you define it like this, where an actor is a class that extends this actor class. And when we create a ping actor, we need to pass it the reference to a pong actor. So this actor ref type here is basically the address that I was talking about before. You need this actor ref if you want to send messages to a pong actor. So what happens here? As the ping actor is created in this particular implementation, it sends 3 messages to the pong actor. And this is the syntax you use in akka. This is the name of the destinatary, the recipient of your message. And then there is an exclamation mark here. And then this is the message that we want to send. We'll see in a bit where this message is defined. And then here, this method here defines the behavior of the ping actor. In this case, it tells us, it's called receive, and it tells us that if we receive a pong message, we'll just log it, println, saying, I received this message. And this pong message, as we were saying earlier, also contains some information. It's just an integer. Where does this come from? A little line below, we have the pong actor here, which we also define by extending the actor class And this actor has an internal state, pings. This is the counter of all the pings that it has received. So the behavior of this actor is that when we receive a ping message, we will just increment the ping counter by 1, and we will send a pong message back to whoever sent us the ping message.
Guarda, anche Asia sente la stessa cosa.
This sender is automatically given to you by the ACA library, where
Sento benissimo,
this
cioè veramente
sender is a type actor ref, so
la sente anche Asia.
same type as Pong actor. Now, this, as you can see, very, very simple. Actors are very simple, very lightweight. And these are the two messages that we can exchange. In this case, we have a ping message, which is a case object and it doesn't carry information beside its own type, and a Pong message, which instead is just a simple class that contains this pings, which is an integer. Now, the way that we instantiate it all, the entry point of our program is this ping pong app. In the beginning, we need to instantiate one actor system. If you want, an actor system is sort of the area, the space, the room where actors live and interact with each other. And once we have instantiated an actor system, we can instantiate first a Pong actor. So this should be a Pong actor with this method here. Then we instantiate a ping actor, passing it the reference to the Pong actor that we have just created, this one. If we run this, what you will see is that, well, it's only 3 things basically. We will see that the ping actor will receive 3 messages back. Let's try.
Muted. Unmuted.
We want to run the 3rd ping pong app. There we go. So the ping actor received 3 subsequent Pong messages in response to his pings with different values as the Pong actor counter increased. Let's clear this and get back to our presentation. There we are. So this was the first example, quite simple. Let's move on to the second reactive pattern that we want to deal with tonight, so-called let it crash. Now this things here starts to get really quite funny. This reactive pattern says prefer a full component restart to complex internal failure handling. What we are really saying here is that eventually in your system failure conditions will occur. It will happen. When this happens, these conditions might be rare and hard to reproduce. How do you fix it? And so sometimes the idea is that it's much better to actually start clean, start fresh, than try to recover from a sketchy state. At that point, think about, remember, catching exceptions. The goal of starting fresh is to wipe all the state that the component has grown into. Because indeed, if you try to recover from a sketchy state, this can be, well, expensive and can generate even more mess. So we just decide to try and start fresh. So how do we get there? This is where the supervisor really comes into play. Imagine that you have 2 actors there, actor 1 and actor 2, and then we have a supervisor that supervises actor 2. Well, actor 1 sends a message to actor 2, asking it to do some computation or some something. Now at this point, as we said, this is like an email. So the actor 1 is totally free. It's doing something else. It's not blocking its execution waiting on the response from actor 2. It's just completely independent. So actor 1 is doing something else while a response might eventually come. Now what happens is that actor 2, as it's doing something, an error occurs, some failure. Now, at this point, instead of trying to deal with it and fix it himself, actor 2 just delegates the failure handling to its supervisor. So it raises an alarm, it raises that message to the supervisor saying, something has happened, so an exception has happened. At this point, the supervisor is in charge of dealing with this failure, and he knows what to do. So maybe fix it or restart it. There's different options. If you're curious, well, there's different options what to do with that. But let's say situation is fixed, and now the error is gone, and actor 2 can resume its work. Send a message to actor 1, which is happy that they received the message. But what's most important here is that beside being happy, the whole process of fixing and recovering from the failure was completely independent and transparent to actor 1. Actor 1 never realized that there was an exception in actor 2. This, for me, it's a major breakthrough with respect to the old way of dealing with exceptions in Java, where basically the user of a service is also the component, is the same component that needs to handle its failure. So in this case, actor 1 doesn't need to know about the possible failures of actor 2. They are completely separated. This leads to a much cleaner and less tangled code. If we try to apply this, for instance, there's this it's funny situation I have. Let's try and map this to a real life example. Let's say that's a developer, and a developer needs some coffee, obviously during the day. Now, what we have there is a very old coffee machine that only accepts exact change. And this is useful to me to introduce, also elaborate a little bit on the difference between errors and failures. So this machine only accepts exact change. Now, first scenario, the user inserts the wrong amount of coins. Well, that's an error. So we are fully entitled to notify the user and say, sorry, you didn't play by the rules. You inserted the wrong amounts of coins. Fine. But how about scenario number 2? The machine is suddenly out of coffee beans. This is a failure. It's not an error. It's not the user's fault. It's some state that in principle shouldn't happen. The machine should always be able to serve coffee. So imagine if we were in this ideal world with the supervisor mechanism that I just illustrated. At this point, the coffee machine could send a message to the supervisor. The supervisor could do on the back a coffee beans injection, and the user would get his coffee in a completely transparent manner. How awesome would that be if all coffee machines worked like that? Now, if we try and sketch this utopian, I would say, situation into our modeling, we have simply something like this. We have a user, a coffee machine with a supervisor. The user can send a give me cafe message to the coffee machine, which in normal conditions will respond with here is your coffee message. If we go and look at the implementation of this, so let me find, there it is. Coffee machine app. Yes, so this is simply the entry point of our program where we instantiate the supervisor. The supervisor actor in here. Yes, the supervisor actor is a very simple actor, just like the ones we've seen before, nothing changes here, that will instantiate both the coffee machine and the user. But also, it will have something new, a so-called supervisor strategy. The supervisor strategy is, well, there's a lot of details and parameters here, but what you really need to know here is that if a out of coffee exception gets thrown by one of its children, it will restart it fresh. Then, well, the supervisor is an actor, so also has a behavior. What happens when it receives a message? In this case, it doesn't do anything, it just prints it out. Now, what the user does in turn is simply, yes, this user, as the user is created, it has the address of the coffee machine, as you remember this actor ref class, and it will send one first message to the coffee machine saying, give me caffeine. And what's interesting to see is that this give me caffeine message takes as a parameter this self, which is an actor ref, is the same type as this. So basically the user is telling the coffee machine, give caffeine to me, and this is my address where you can deliver the coffee. We'll see in a second why we need that. Now, this user seems to be quite addicted to coffee, as every time that it receives here is your coffee message back, it will just ask another one after 2 seconds. It will send another give me caffeine message to the coffee machine. Now, the coffee machine is where the real meat is. This coffee machine is an actor, like the other ones. It has an internal state caffeine reserve that when the actor starts is equal to 4. Every time that we receive a give me caffeine message from a user, remember this was the actor ref from earlier, we will check if we do have coffee to give. So if our caffeine reserve is equal to 0, then it's bad and we will throw an out of coffee exception. Otherwise, we will just decrease our coffee reserve and send to the user a here is your coffee message. Now, what we are going to see is that so after 4 messages, the user will trigger basically a crash. It will ask more coffee and the coffee machine doesn't have it anymore. So at that point, the coffee machine will fail. It will be restarted by the supervisor, and in doing this, the actors, they have some life cycle hooks. So this method, overridden pre-restart, is a method that is invoked on the actor when it's about to restart that contains the message that caused the failure. So what we can do here, when the machine is being restarted, we will have access to the message that made us fail. In that message, there was the address of the user who asked us coffee. So what we are doing here, we are sending to ourselves, so the coffee machine sends to ourselves this message here. And the result behavior is that the user will not realize that the coffee machine has been restarted. If we try to run this, spt run again, you will see a lot of logs. Coffee machine app is number 2. So the user is receiving and asking cups of coffee, until the point, there we go. What's happening here is very interesting. I'll stop this. It was a cycle anyway. Here at this point, coffee machine went out of coffee and failed, which was detected by the supervisor, restarted it. This was the reason why it failed. It's an out of coffee exception. And after restart, the caffeine reserve was restored, fresh, to 4. Then the coffee machine sent to itself the give me caffeine message that caused it to fail, and the user transparently receives its desired cup of coffee. Now, so this was a demo about resilience and transparency, failure transparency. That was it. If we go now back to our patterns, let's look at the third one. And third and last one, a circuit breaker. This pattern says protect services by breaking the connections to their users during prolonged failure conditions. So in order to explain this, what we can imagine is a different situation where the same imagine that we are in a web situation where you have some web client, some website that user ask HTTP requests. This web client actor will ask to the database actor to fetch some data, and this database actor is doing some I/O operations from a database. So those operations are risky. We all know that. They are long, they're blocking, and everything that we know, all the bad things. So yes, scenario is user wants to get some data. User makes a GET request. Web client actor forwards, sends a message to the DB actor, give me some data. And at this point, the web client actor is waiting because they're completely separated, as we mentioned before. And as the DB actor is trying to fetch data, a failure occurs in the database. Now, at this point, the database actor is not able to send a response back. So what is happening after a little bit is that the web client actor will trigger a timeout, and say 10 seconds later, the user will see something on his web page. So that's obviously bad. That's not responsive at all. What the user will do at this point, you probably know that, immediately as the timeout occurs, it will hit refresh, another request will come in, another message to the DB actor, waiting, and 10 seconds later, timeout. If you didn't notice any difference with the first attempt, you're right, because there weren't any. And at this point, the user will likely leave the website or try again with another refresh, which will lead to exactly the same situation. That is why we introduced a circuit breaker component. A circuit breaker component comes from the Akai library directly. You don't have to implement it yourself. It's a component that sits in between two actors, and it basically it's a gateway. It's a gateway. So scenario is this. We receive a GET request from our user. The web client actor forwards a message to the DB actor, and this message goes through the circuit breaker. Then we have a situation where, again, the web client actor is just waiting. Situation where the database has a failure. And just like the first time, after 10 seconds, we will send a timeout back after 10 seconds of a blank page. So you will say, okay, but this is the same as before. It's not quite the same as before, because what's different is in all this, the circuit breaker has detected a timeout and opened so-called the circuit breaker. What it means is that any further request that comes in will be directly responded with a failure. So the actual situation is that the user will immediately hit refresh, like all users do, will get a GET request, will forward the request to the circuit breaker, but the circuit breaker will immediately respond with a failure notification, immediately. And so that we can immediately tell our user that their service is unavailable. Immediately. And this is much better. Even if we haven't provided content because it was unavailable, we still reacted immediately, which is a great improvement. So yes, benefits of this pattern are that you get an immediate response towards the responsive principle, but also that you don't hammer the failing service with requests. You just give it time to recover. You've protected this failing service from being hammered with requests that will most likely fail. And what happens after a while is that a circuit breaker can be configured. So after a while, let's say you give some time to recover, and then at this point, when we get our flow of requests from a user, we will get a request back, and we're finally able to send a 200 OK response back. Let's quickly check how this would work in our previous coffee machine example. In this case, we made things a little bit more fancy, where our coffee machine now is sort of split in two. You have a coffee machine actor there in the middle, which is sort of the user interface, and internally there's a coffee brewer, so some component that brews the actual coffee. At this point, we can see that the message flows is give me caffeine from a user to the coffee machine as before. There's this internal brew coffee message sent. We'll get some coffee brewed message back, and the user will get his coffee. But by doing this, we'll also put a circuit breaker there in the middle between the coffee machine and this coffee brewer, because we know that if something goes wrong in the coffee brewer, it's an old component made of steel and rusty. It takes 20 seconds to recover. So let's see how that looks like in code. There we go. If you really need to find it, there it is. Circuit breaker example. User and supervisor are very similar to what we've seen before. So the user will have a coffee machine reference to which it asks for give me caffeine. Now there's a little something different, is that the user now is also prepared to receive an out of order message, a failure. The supervisor it's pretty much exactly the same. It also supervises the coffee brewer in this case. And same as before, if we get an out of coffee exception, we'll just restart the failing actor. The coffee machine. The coffee machine now is a little more complicated because it embeds a circuit breaker. This also comes from the Akka library, where this is all timeouts that you can set. These are callbacks when the circuit breaker opens, closes, and so on. So what happens here? This is a little more interesting. If the user has sent us the wrong amount of euros, a coffee costs 2 euros, let's say, we send back a message saying you gave us an invalid amount of euros. That's the coffee machine and only accept exact change. Otherwise, we will ask the coffee brewer, we will send a message saying brew coffee for us, please. And this interrogation mark, this question mark, is the way in Akka where you can send a message to an actor, in this case a coffee brewer, specifying that you expect a response and that this response should come within a time period of 8 seconds. So what we're doing here is that we're asking the coffee brewer to brew us some coffee. Normally, we would get a coffee brewed message back, and in that case, we send coffee to the user in this line. But something could go wrong. If a timeout occurs, the coffee brewer doesn't respond in a timely fashion, we'll send a sorry, something is wrong message to our user. And if the circuit breaker is open and we get this failure here, we will just display an out of order message. So as you can imagine, let's try to run quickly through this code because I think we're also running out of time. There we go. What you will see is that the first time that the coffee brewer crashes, the user will hang on there for maybe as long as 8 seconds, waiting for the machine to respond. But subsequent calls will immediately tell the user that something is wrong. So let's try to run this. Yeah, there we go. Normal cycle. Everything's working. Soon, yes, we got an out of coffee exception. The coffee brewer will now take 20 seconds to restart. Yeah. Now, what is happening here is that the user first complained because we were slow telling him, wow, that took a while. Tried again, but the circuit breaker is open, so it immediately gets an out of order message. Now at this point, based on the timeouts that we set, the circuit breaker will go open again, and when the coffee brewer has started again, and yeah, well, the cycle is the same, fail again and recover again. So the circuit breaker is ready for you to use, and it's quite a simple component, but really, really powerful when it's a question of protecting your systems. That was all for me. I put together a couple of useful references here. The Reactive Manifesto, didn't put links, but you can just Google them. That Reactive Design Patterns book, I really highly recommend it. The Reactive Programming versus Reactive System is a very recent article for Jonas Bohner and Victor Klang, two very prominent Lightband people. Jonas Bohner is actually the CTO and founder. And finally, Akka in Action is a book about the toolkit that I was talking about in the beginning. Time for questions. I see only one question. Jordi asks, will the code be online somewhere? Yes, definitely. The code is actually already online. It's on my GitHub repository, and let me try to answer this question. Oh, well, it's, well, just if you search for TicoFab, that's my, my GitHub account. Any other questions? Nothing coming. Then, well, everybody, thanks for joining this webinar tonight, and I hope you had fun. Oh, wait, there is one question. What to Akka or RabbitMQ? Right, yeah, very good question. Bas is asking us if, well, basically, I guess the differences between Akka and RabbitMQ. RabbitMQ belongs to the first category that we looked at the beginning, an event queue, where messages are sent anonymously and they are observed by someone. Akka also implements something like this internally, but yeah, they are very different tools for different purposes. I think this is it. So thanks everybody for attending, and see you at the CodeMotion Amsterdam conference in May. Have a nice night.